Hi guys, in this video we are going to analyze the common gate transistor with an internal output resistance. Common gate amplifier senses the input at the source and the output is taken out of the drain while the gate terminal is held at AC ground in small signal model. That means it is held at a DC bias voltage. Here I've drawn the common gate amplifier's small signal model, and I have included the internal output resistance RO that is connected between the drain terminal and the source terminal, and the RD is connected to the drain and to VDD, and VDD is grounded in the small signal model. As usual, we will analyze the three important parameters, which is the voltage gain, input resistance, and the output resistance. Let's start with the output resistance R0, Rout, because this is the most easiest derivation. So I have made changes in the small signal model. To find the output resistance, we need to ground the input, and a test voltage is connected to the drain terminal. So in order to calculate the output resistance Rout can be written as V test divided by I test. By applying KCL, we get the I test, which is the current that is getting split into these branches. I test is equal to V test divided by RD plus V test divided by RO plus GM/VGS. The gate source voltage is the gate voltage minus the source voltage. Here the gate is grounded and the source terminal is also grounded. So VGS is 0. I test can be derived as V test into 1 divided by RD plus 1 divided by R0. By rearranging these terms, we get that Rout is equal to RD parallel to R0. And mostly in cases where R0 is much greater than RD, so R0 is almost equivalent to RD, which is similar to the common gate amplifier without an internal output resistance. Now let's calculate the input resistance Rn. The input resistance Rn is given as a test voltage divided by a test current that is injected into the source terminal. So instead of V test voltage is injected into the source terminal, and I have used a KCL to find the current equation. So I test is given as minus of GM/VGS plus the current in this branch, which can be given as V test minus V out divided by RO. Let's try to do KCL at this node. This was the first node that we calculated. This is the node number 2. And if we apply KCL here, we get V out divided by RD plus V out minus V test divided by R0 plus GM/VGS, which is the current in this branch. That is equal to 0. We know that the gate source voltage can be given as the gate voltage minus the source voltage, which is the negative test voltage. So by rearranging all these terms and reducing the formula, we get V test divided by I test is equal to RD plus R0 divided by 1 plus GM into R0. Rn is equal to RD plus R0 divided by 1 plus GM into R0. So without the internal output resistance, Rn is equal to 1 by GM, which we derived in the previous video. This Rn value can be realized if RO tends to infinity, and Rn will be equal to RO divided by GM into R0, because RD can be neglected and 1 can also be neglected. So RO divided by GM into RO, which is equal to 1 by GM. Now if you take the equation number 1 that we derived, which is the KCL that we applied to node 2, which is the KCL that we applied here. I have rewritten the equation here. So we can see that in order to find the voltage gain is basically V out divided by V in. So instead of the test voltage that we have given into the source terminal to find the input resistance, all we need to give is an input voltage at the source terminal to find the voltage gain. So essentially we can replace V test as V in. So I have replaced V test as V in, and I rearranged the terms. So we get V out is equal to V in into Gm plus 1 by Ro divided by 1 by Rd plus 1 by Ro. And by multiplying the numerator and denominator with Ro and dividing both sides by V in, we get the voltage gain as 1 plus Gm into Ro divided by 1 plus Ro divided by Rd. If Ro tends to infinity, the voltage gain becomes Gm into Ro divided by Ro by Rd, which can be written as Gm into Rd. So these are all the important analysis for a common gate amplifier with Ro, and we'll discuss further topics in the upcoming videos. Thank you so much for watching. Bye.